Okay, let's start. So sorry for the delay. I guess I'm audible. Should be audible. Okay, so I see there's no one. But okay, but according to time, I should start now. Whoever joins later will give you an introduction. So this is like week 2 for the course Introductory Mathematical Methods for Biologists. This course is by Professor Ranjit from IIT IIT Bombay, and I am Jagriti, a fourth year PhD student in Department of Biological Engineering at IIT Gandhinagar. So my research is based on quantitative ultrasound for soft tissue characterization. I work on signal and image based processing techniques for tissue characterization and to see disease progression and how to early detect it. So that's my field of research, and this is what I'll be TAing for. So sorry for the delay. Okay, let's start. So last time I could not tell you all, but this is the book reference that you should follow. That is being given by Professor Ranjit on the NPTEL course platform. That's Mathematics for Biological Scientists, and it's by this Galden Science. So the first author here is Aitken. So you can go and refer to the PDF copy of the book. However, you'll get it on other sources. But I do think so that on your particular on your respective institutes you might have different separate copies for the same if you are in if you do have a biological department in your institute. So last time we directly talked about sine and cos, but it wasn't very clear that if you all know. So these are like trigonometric identities, all like sine, cos, tan, cot, cosec, and sec. And then there's also so with respect to degrees and angles, we saw that how one varies. So if one particular whole degree, one radiant is like one whole complete, that's 360 of it. So if you convert a degree from radiant, you do pi by 360 or 360 by pi accordingly. And here you see that if I change a degree from 0 to 270 degree, accordingly the radiant form of it also. So pi is 180. If you divide that by 6, that becomes 30, right? So that's itself. So here itself the conversion you can see. Okay. Make it convenient for me to write. I hope this is fine with all of you. Um, Let me check. Okay. So here, so if you see over here, how sine goes from 0 to 90 is nothing but it goes in increasing fashion. So it increases and goes till 1. Whereas for cos, if you see, it starts from 1 and then decreases back to 0. Whereas for other, so tan is nothing but it's a ratio of sine and cos. Okay. Now, how sine came and from where, what's the definition of sine? We'll also see that in so in consecutive classes. So it's nothing but everything comes from hypotenuse, adjacents, those. So if you know right angle Pythagoras theorem, you'll be able to catch up with this. But this is just to get you know because soon like we are having staggered thing of everything added together. It's not coming from 1 0 to start. So that's why like a brush up into these things and how it came from where and what's actually sine cos in terms of triangles. I'll let you know. Okay, so for now, just keep that. Okay, so or else I can also tell you now itself. So if you have a triangle, a right angle triangle here, this is 90 degree. In this particular case, if you take theta across this particular, so if you want to take sine theta, that is, and now let's give them some value. So this is perpendicular, hypotenuse, and let's say this is base, so B. So that would be sine theta would be nothing but P by H, right? So that is always hypotenuse by, okay. Okay, so this is and this is opposite by hypotenuse. Whereas if you do cos theta, that is nothing but adjacent by hypotenuse. So that is your adjacent to this particular angle is base by hypotenuse. Your opposite to this angle was perpendicular by hypotenuse. So this is how you have these. Then when you take tan, tan is nothing but the ratio of both sine and cos. So that takes us as sine and cos, the ratio of both of them. Then if you have cot, sorry. we have cot theta as nothing but inverse of tan theta. So this inverse is not like tan inverse theta. This is like actual 1 by tan theta. Okay. That also means something else. Then you have cosec. It is inverse of sine theta. Not inverse, I should say, but okay. That's why it is like that. And then if you have sec theta, that is inverse of cos theta. Okay, so these are like all trigonometric identities. So there's like one particular thing that me, when I was a kid, I used to remember that if you take this, it is something as something for you to help you remember that in which particular quadrant, which particular trigonometric identities get converted from one form to another form. Okay, so I'll just this up. Okay. So let's say this is your 0, then this is your pi by 2. Okay, I hope that's visible. Yeah. Then this is your pi, and then this is your 3 pi by 2, and then you again go back to 2 pi. Okay, so it's like all students take and then care. Okay, so that means all, as in for all identities are positive in this particular domain when you go from 0 to pi by 2, or it's the other way from 2 pi to pi by 2, or pi by 2 to 2 pi. Okay, so that's in conversion. So whenever your theta is changing from this particular angles, they all would be positive in this particular quadrant, right? Then when you go student, so that is nothing but you only have sine terms, and then the terms which are getting converted here, those will be positives. Here, those are tan terms, and here those are like see this. So that's cot, cosec. Here it's also sec. So the terms are converted here. Okay, now if you go from this particular domain to this domain, let's say cos of this pi by 2 plus theta, that converts you to back to sine theta. So there are identities there, but here they're like just briefing you into this one so that you won't find it very new when we go around them. Okay, so similarly, you can see, so tan is nothing but the ratio of both of them. So 0 by 1 is always 0. Then again, this by this is 1 by root 3. This by this is again 1. This by this is like root 3. Again, 1 by 0 is not defined. Okay, so again, tan, cot theta would be inverse of all tan. Cosec is directly inverse of the sine. Sec is inverse of this particular sec. Okay, so that's how all different trigonometric identities are, and this is what I wanted to show it to you. So we saw that day that sine is an odd function and cos is an even function. Now, if you take their so an odd function and sine function together gives you an odd function. So that's like nothing but plus minus is always minus like that. So this is your odd function. Following to it, this is also odd function. Now sec is like inverse of cos. So that would be an even function. And this is an odd function. There are some half angle formulas to it. At this particular point, it's too rushing into it, but it's fine if you don't look at these ones. But there are these identities where sine square plus cos square is 1. Then you have 1 plus. So these are all like proven you right angle theorems proof. You can always go around and check like, okay, base by hypotenuse, perpendicular by hypotenuse. If you do those things, you'll get this identities true there. These are like reciprocal that what I just told you. These were like, yeah. So if cot is 1 by tan theta, that's essentially cos by sine theta. And these were the half angle identities, so cos co-function identities that I was saying. So if you have something which is in between, so cos of this, so that will convert it into sine, whereas sine converts into cos. Now these all are positive in this particular domain and gets converted back into their own form. Whereas second cosec gets into their own, sine cos into them, and tan and cot. Okay. So last time someone asked me that from there this Taylor series, and so how did we give an expansion of e raised to x, then we had expansions for sin x, we also had expansions for cos x, and then I just told that okay, this is just how it is, and derivations at that particular point I wasn't aware of. So it's something which is involving a derivative here, then you have a factorial here, and then you have a summation in this particular form to finally take it around. So that's nothing but a summation series which goes from 0 to infinity. So this is Taylor series, which says that you take a function of nth derivative of this particular a, evaluate it at a by nth factorial, and then x minus a whole raised to n. Whereas Maclaurin series is another subpart of this Taylor series, which is nothing but evaluated at a equals to 0. So if you just look at in between both of them, there's only this one particular difference, that this is evaluated at a equals to 0. Okay, so I'll just give you one example for one specific series, that how to solve it, and then later all others you can try using the formula that's written over here. Okay, just add a page. So these were like the series that we saw, the expansions. Let's take this e raised to x for simplicity. Okay, so we'll just take that one. Let's see if it can be copied here. It cannot. Okay, so if we can add a page. Okay. Great. So we are able to add a page here. Not wait, take it back. Cool. So let's see if I take this e raised to x term. Okay. So if I have a function, feel free to interrupt me. I guess we only have two students here. So if you have any doubts, you can interrupt me anytime you want. Okay. So if I have f of x is equals to e raised to x, okay. Now you see what the this particular formula for Taylor series was. It's this one, okay. So that goes from a summation of n equals to 0 to infinity. Then you have nth derivative of this particular function, evaluate it at a, then n factorial, and then you have, oh, sorry, I guess if someone's also saying anything, I won't. Okay, cool. And then you have x minus a whole raised to n. Okay, so this is your thing. Now you look over here, if we just expand this particular form, we are not looking at e raised to x yet, okay? So we'll give it as f of x is equals to, we won't care about the other terms yet, we'll just see for this particular term. So how it goes, see, if it's 0, what will happen? 0th factorial is 1, that we saw that day. And if this is 0, that is nothing but x raised to n, and this is 0, is 0th derivative against it. So we'll only have a function that is at 0, big, right? Because a derivative across a constant would be 0, so we won't have anything, so that would be 0. Then what would be the second one? That would be the first derivative times x, right? Because this first derivative evaluated at 0, and this a, that is nothing but here, so that would be x, right? Then let's say the second one, then third one, okay, and so on. So that's how you do it. Now if I just look at it for simplicity, let's do something as, this is my a0, okay, this f of 0. Then this is my a1, so that means the function evaluated at the derivative of the function evaluated at 0, I'm denoting at a1, okay. Then a1x, let's say a2x square, and then a3x cube, and now you know the series can go on forever, right? So I'm not deliberately giving it the parameters according to the formula over here. You can directly input it in, but whenever you have another explicit function, this way going makes it much more easy for you instead of doing it direct this way. Now, if you have this particular e raised to x, now what will you do? First is nothing but you evaluate the function at 0, because this particular term is directly at 0. So what you do, now e raised to x is equals to this all term you have. Now x equals to 0 makes all of the others as 0. And this term is nothing but a naught itself. So this is 0 is nothing but 1. So that gives you 1. Okay. So we got a first term. Now we want a second term, and we know that, okay. Now this is just assumptions, but you all don't know at this particular point. That's why it's told that some things are here, like coming in and clashing in from here and there. So we haven't learned derivatives yet. But for this particular sake, I don't know how to say these things, but yeah. Remember that derivative of e raised to x is e raised to x. We'll prove this, why this is as so. But yeah. This is that derivative of e raised to x keeps as e raised to x. Okay, there are no changes to this particular function. So let's take derivative of one of these functions, and then again, I guess I'll have to tell you another formula over here also. If you have gone to the online classes, the lectures, then you might be aware that if you have, let's say, something as x raised to n, that goes as n, then x, then n minus 1. Okay, so wherever you have this x raised to 2, that would be 2x power 1. If you have x cubed, it would be 3x power 2, right? So that's n minus 1 there. Now, if we take a first derivative over here, this e raised to x keeps as e raised to x. Derivative of a constant function is 0, right? Uh, it feels that I'm teaching derivative here itself, but if I don't tell you, then it would. Okay, so derivative of a constant function is 0. So this goes as 0, this particular term. Here it would be a1, and the rest will be 2a2x. Then this would be 3a3x2 plus this would be 4a4x cube and plus so on, right? So it goes as this. Now you evaluate it at 0. So that would be e raised to x. So this is 0 is equals to a1. So you have a1 is equals to 1. Okay. So that is also one that you got. Now what next? Next, you have other second term. We'll just do till second term, and then I guess you know the thing that you have to do again. So let's take the derivative once more. Now, if we do this for this particular term, it would be a constant. So that's 0. This is 2a2 plus this is so 3 times 2a3 x raised to 1. Okay. This is 4 times 3 times a4 x raised to 2 and so on. Right. So you have the first term, evaluate this at 0. You get 1 by 2 is equals to a2. Now you look at this particular form. How do we write it? This is the actual form that we started with. So if we go e raised to x is equals to a0 is nothing but 1 plus a1 is nothing but 1. So 1 times x plus our a2 is nothing but what is our a2? 2. So that is 1 by 2 times x square and plus so on. Right. So now this 1 was nothing but essentially here we had a 1. So this is 1 by 1th factorial. This becomes 2th factorial, that's 2, right? Now, if you do for another one also, look at here, you have 3 and 2. So that becomes 3 factorial. Now, this will also, if it goes on, it will become 4 times 3 times 2. So that will become as 4 factorial. So I hope this is like clear. So from there, this is how we derive a Taylor series. And accordingly, you can do for others. Now, if you want to check, here's like 1 plus x squared by 2 factorial, x cubed by 3 factorial. That's how it comes. It's also easy to do for all other terms right here. But for doing that, you need to know how to take a derivative. So that we'll see in this particular class that what are derivatives and how to take derivatives. Okay. So this is how Taylor series comes from. And that's why in the first class, we didn't introduce from where it is coming from, but that's a formula for it. If you want to calculate it, you can calculate it this way. It's pretty much simple. Okay. So now let's see. Okay. So we won't directly go into this derivatives, but I'll show you one more thing before that. So this is how the week started, week 6 started, that if you have an image, a image is a 2D something, right? Here. Image is a 2D object or a 2D subject, right? Where you have a x dimension and you have a y dimension to it. Now, when you have something as this, how do you represent it in terms, mathematical terms or expressions? Because eventually, if you do some heat maps or if you do an image, if you get some microscopy image, if you stain your cells with some dye, a fluorescent dye or something, if you want to quantify its intensity, the fluorescence that it's coming it from, how do you quantify those terms and how do you relate it back to? So it's like, again, if you do some assays where you have protein and you need to quantify the concentration of it, where it's higher, where it's lesser, you might want to do UV visit, like UV vis spectroscopy. But in those techniques also, you need to study the graphs. Now, graphs we saw last time, but after those things, there comes an image. Now, how do you interpret that image? So when we have something like this, initially we had saw something as y is equals to f of x, and that y equals to f of x was nothing but a line that is passing through origin, right? And if we did y is equals to x, its slope was 1. right? I hope you all remember till this particular point. If not, nudge me in between. Then whenever you have a function, a image, a 2D function, it can be represented as z x comma y, right? You can write it like this. And basically in online class, there was a example that was given from prof. That was this one. Where did it go? Documents. Yeah. So one of the examples that was given was here, this one, where you have z is equals to x 10 minus 2x. So here you see that as in how the intensity is higher, the value is higher. So it's nothing but based on of in a color bar. So here the plot I've plotted in Excel, I've just given some conditional formatting to it. So the value is higher, so I've taken a red to green color plot. So values lesser would be red, and then variance of red, variance of green, and then accordingly variance of red. So here you see the value decreases. Now at this particular point, this particular function is only dependent on x. It has nothing to do with y. So whenever it would be dependent on y, it would show the variations against it. Similarly here, if you see, it has variations with respect to y. That's why in here, to this points where the gradients are lighter, they mix up to a darker gradient, right? So they both have an effect into it. So that's how like if you have two functions at a time, two variables at a time, one dependent, another independent, in this case both are dependent variable. So for your function z, this is nothing but it's a function of z is a function of x comma y. So z is a dependent variable, whereas this x and y are both independent variable in this particular case. Okay, so you can quantify those things from there, and then accordingly, if you see, we have the sine and cos x. So if you do it, so if you have one function against this particular, another function against this, the third function can also be the summation of both of them, right? So accordingly, you have like 2D functions and there are matrices against it. So you can represent them. Now with that, I'd like to show you derivatives. So that was just an intro into 2D functions. So this is derivatives. So what is a derivative? For now, what we were trying to do, we were trying to take a slope, right? And what that slope was, if you have something, let's say if I have a curve like this, okay? I want to evaluate something, the slope at this point. Okay. Yes, right. So this is my x, this is my y. So let's say for this particular x, this would be some delta x, some smaller range of x, and this would be delta y. Now, what is slope? Slope is nothing but change in y with respect to change in x, right? So that way, my slope is nothing but delta y by delta x, right? And this is how you quantify the slope as. So that's how it is changing. Now, in this particular case, your slope was delta y by delta x, so it is independent of this particular term x. Right? So it is independent of x. So how do you evaluate derivatives? Derivatives, if you want to. So then again in class, prof have shown different examples for x square, x cube. So I won't repeat all of them. So if you change and change and change how you see those. So effectively the meaning over here is if you take a very smaller range of your derivative. So I'll just show it for a smaller range. So let's say if this particular range for me is delta x and this particular range for me is delta y. So how small those delta x, this range can it be, that will give you an accurate derivative or that particular slope. So derivative is nothing but slope. Sorry for the disturbance. There is a tournament going down there. Okay. So how do you evaluate it? You take a function. So this x plus dx of a one particular function. So see, this is, don't get confused in here. This is nothing but function of something. So that is nothing but, let's say it can be y of one particular quantity, let's say y2 minus this x. So can be y1 divided by delta x. So that is x2 minus x1. So 2 and 1 I'm just giving here for some number's sake. So it can be b and a and can be a and b like that. So there we want to do that if my limit or the delta x, it ranges to 0, make it as small as possible. If that particular function is as small, the slope that you get, the derivative that you will get is nothing but the accurate derivative for that particular curve. right? And then if you do it for, so when we had y is equals to x, it was nothing but independent of x, and it was just 1. When if you do it for this particular curves, it is, these are nothing but non-linear. So for non-linear curves, your derivative is nothing but always non-zero. It is non-zero and it's again dependent on x. Right? It's dependent on x. So here is something else. So I'll just give you some examples in between so that you can again relate it with the lecture slides. Add a page in between. Okay, so we saw this, and previously I gave you an equation for solving a derivative, how to calculate a derivative. So if you have a function y, if you want to take derivative of this particular function y, so this is like bare minimum example definition for it. So if you do it as n x n minus 1, given your y is equals to x raised to n. Sorry, I forgot that. So it would be like this, right? So let's just take few examples here to refresh your memory. So y, if let's say y is equals to x square, can any one of you tell me what would be its derivative? Dy by dx. It's pretty straightforward. We did it for e raised to x now. What it would be? Ah, yes, yes, go forward. You can directly unmute yourself.
Yeah, it will be 2x.
Yeah, exactly. It would be 2x. Similarly, for other functions, if you do, it's, I think so for now, you know it. So that would be like, let's say 3x square. So these are like non-linear functions, and you see that it's always dependent on x. Whereas when we did something as y is equals to x, this had nothing to do with it. So it gave me a slope that is equals to 1. So it is independent of it. So at this particular point, the gist that you have to take is for nonlinear functions, it's dependent on x, and it has a variation of degree that it won't give you a slope that is non-zero. So your slope or this particular derivative won't be equal to 0 for nonlinear functions, whereas for linear functions it can be, right? So that is how we took it off. Now there are some rules for derivatives. So if I have it here, derivative rules. Okay. So before doing that, we'll just see that, okay, if you have a function, we'll go from like a constant range. We directly won't go into formulas. So let's say if we have some functions like this, okay. So here, I'll just use a pointer because they have a nice arrows here. So this is nothing but decreasing from this particular case, right? So when you have some decreasing function, let's just mark it this ones and this ones, right? Now these pointer will, yeah. So when it decreases, now you see from one particular point to another point, this function is now cross zero at this particular point, and this is decreasing. This decreasing is giving us a negative slope, right? Again, at this point is nothing but constant, and then it's going to zero. So the slope is all about increasing or decreasing at a linear rate. So then you have a constant slope here, then made it as zero again. Then you have an increasing slope, but this is also constant, but it's increasing slope. And now here it's crossing zero again. So here I'm crossing zero and then making it constant and then again zero after some point because it's not going anywhere, not showing me any fluctuation. So that's how a positive slope I'm getting towards the end. Right. Similarly, if I have an increasing function, now this again it's crossing zero, pausing to zero. So now at this particular point, when I'm taking a slope against this line, that will give me as a zero, right? So that's a constant function. So this here and a constant function that I'm getting here. Now here was a point that after which it's crossing zero. So that is a decreasing slope. And again, after that decreasing slope, it is going on forward. So this again a constant for that particular decreasing slope, this constant value here it cross zero and then this. So if even if you don't know derivatives of certain functions, what you can do is like just see the trend, how it is going for and how it's looking into the function, right? Similarly here, now this is an example that I wanted to give for sine and cos. So sine and cos are like derivatives of each other, but since one is an even function, another is an odd function, you always have a sine role to play in here. But here we'll just take a positive way forward, like we'll say the derivative of sine is cos. So how do you see it, right? Now you see from this point, this is nothing but increasing slope. How we did in the previous slide. So this is an increasing slope. So for this increasing slope, you'll get a constant value. But since now these functions are nothing but discretized and they are continuous functions as a function of x, so you have many values in there. So you can't directly make a square up there. That square will also have a curve nature to it because it is evaluated at even like 0.000 point values. So it won't directly be a square. In this particular case also, even if it was in different function, this would have been evaluated as something as this. Okay, so don't get confused in between these points. So here, just for visualization that how a derivative of sine is cos. Okay, sorry. So if you see over here, this is nothing but 0. Now this is an increasing slope. After this point, it's here. So for this increasing slope, we now know that it has reached to a point. So it will start at a constant value, right? So it is an increasing slope. We have a constant point to it. So this is a constant point that we had. Again, after that point, it is decreasing, right? So now this is decreasing. So for us also, it will cross a 0, right? It decreased. Now it is increasing again. So for us also, it will increase again. So that's the difference in between sine and cos. Only the function at which it has started its value, after which it follows a similar trend, right? Now if you take it inversely, right? Now if you see the trend over here, now if this goes first and this comes second, in this particular point you had this particular quadrant, that's why that's an odd function and you have a minus sign before it. So you try to do it yourself. You just make both of the plots and then see that how the other one gives rise to the first one, because now you have this particular quadrant to it. Now it will be evaluated from this point and not this point here itself. So from this point, because sine starts from 0, whereas cos starts from 1 itself. Okay. One more example. So this kind of function is called as sawtooth. Okay. And in biology also, you see different examples for it. So sort of kind of functions you see in growth assays, growth curves, whereas microtubule assays. So if you see how one thing is changing over time, getting stretched over time. Again, in electrical, you see something as charging of a capacitor. If it charges, discharges at that particular point. So it's not exactly sawtooth, it's more of an exponential behavior. But when you discretize it, you'll get a sawtooth behavior there. So here again, if you see it is now increasing, so that's a constant slope. It is positive here and then it's decreasing back. So again, it will decrease. Then this particular slope is constant. Then this is an increasing slope constant. So we gave a constant slope to it. So just make an intervals, line, dashes, and just try and make it. So this is as simple as that. So we'll just see the formulas over here. So derivative of f is the rate of change of f. So that is nothing but you take this particular limit as small as possible. So you evaluate the function at these 1 delta x points and then differentiate it with respect to the initial point it was at, right? Now when the limit was higher, you won't get an accurate slope if you want to, because now it has this particular trend coming into. When you make it this particular limit as small as possible, you would be able to extract the slope against it, right? This. So when you made a limit as small as possible where delta x tends to 0, so this limit is nothing but it just tells you that one particular this variable is tending to some value, some constant that you want to evaluate it at, right? So here also we want to make this range as small as possible and then doing it. So that's how the derivative comes from. So these are like just the things given again. So you have derivative like this. It is essentially slope. Now, if you want to evaluate it at, so that's what I told you, that this was evaluated at 0. You can evaluate it at any other point. If you do it at a, this would be f of x minus f of a, and where x tends to a. So when it will tend to a, it would be nothing but 0. So below term would be 0. It won't be defined. So that is the point where you'll get the slope as accurate as possible, right? Now, there are different rules to differentiation. The first one that you already know because you gave an answer for it. So that's n x n minus 1. The second one is like a product rule. So that you go as like u dv by dx, then v du by dx. Then you have a differentiation rule where you have like, not differentiation, division rule. So, or this quotient rule. What you do in this case is you take the first one, the numerator. So this numerator is first derivative. You take a derivative of it and keep the denominator as it is. Then subtract, keep the numerator as it is, and take the derivative of the denominator divided by v square, right? So these identities also have their own derivations, but at this particular case, you just remember the formulas. These are like, if you do it on practice, it would be easy for you to solve them. So if you want to do it, like you can try an example for 1 by x for this particular case. You can try for, let's say, x time x for this particular case. This you already know. Then this also you know. So in this particular case, u wasn't a function of x. So how did you do it? So this a is nothing but that we knew. So we'll do it like change in power and then again differentiate it. So that won't end at this particular point. The power will also change and this will also change. So that's a chain rule that we see. Then you know that ax will become as a. Then if you take for a constant, that is 0. And then if you have two terms in addition, it can be separated. So this derivatives are separable functions. And then if you have subtraction, can also be separated, right? So similar rules won't follow with log, but rules following here for derivatives, okay, for differentiation. So I guess that's pretty much it. And for sine and cos we saw. Okay. So let's take an example at this particular point. We saw the rules till now. We saw how to compute the slopes. So let's see if we can do the derivative for e raised to x, right? For e raised to x. So now we know what e raised to x goes as 1 plus x2 by 2 factorial plus x3 by 3 factorial plus x4 by 4 factorial and so on, right? So I just told you for derivative for this one, it continues to be the similar function. Now why so? We'll see that if we take derivative of this one function, for 1, that is a constant, that is 0. For x, it is 1. For x squared, that becomes 2 times x, and then you have a 2 factorial here. Then you have 3 times x2 by 3 factorial here, right? And then so on. So now if you see, this is 0, it got cancelled. This is 2 by 2 because that's 2 times 1. So this is nothing but x. So you have 1 plus x plus. Now 3 by 3. So 3 factorial is what? 3 factorial is nothing but 3 times 2 times 1. So 3 got cancelled. You have 2 times 1. So that is x square by 2 factorial and so on. So this is how you saw that this term also became equivalent to how you had previously. So these terms are matching. So that is e raised to x, right? So I hope that's clear. We can take another example for derivative of sin x if you want. So how does sin x goes? Sin x is nothing but x minus x cube. I also forgot. I don't remember these formulas, extensions of them. X minus x cube. Okay. Here. So we have x minus x cube by 3 factorial plus x raised to 5 by 5 factorial minus x raised to 7 by 7 factorial plus so on, right? So how do you do it for this one? Okay. So you take derivative of this of sin x. So what would be derivative of x? That would be 1 minus, this is 3x2 by 3, 2, 1. Okay, we'll just evaluate the factorials itself. Then this is like 5x4 by 5, 4, and it would be a fourth factorial, right? And then minus, this would be 7, and then this would be like x raised to 6 divided by 7 times 6 factorial, right? So now we see, this is like 1 minus x square by 2 factorial, right? Then you have here is plus x raised to 4 by 4 factorial. Then you have minus x raised to 6 by 6 factorial. Now you see this one, what it matches to. So you have a cos here. That's like minus x squared plus x raised to 4 minus x raised to 6. Now you see the function here that we just did, right? So derivative of sin x is nothing but cos x. Similarly, if you do this at home, derivative of cos x, you just try it on your own. It would be easy and you'll feel it. And now, since now you know derivatives, I'll also encourage you to study log, because I don't see that a prof has given. But whenever we see it, I'll also tell you that okay, how to do these things more into. So I'll also tell the formulas for the same and how it came through. But if you also have an understanding, it would be better for you to understand the lectures, or else it would be too jumpy for you from here and there. So study log, study derivatives for log, and log identities. So I'm not saying some hi-fi identities, but I'm just saying how to solve logs. Let's say if you have log of that day, last day I told you that how the identity evolves, like this one. Then you have something as a by b, if it's a separable function or not, if it's like this, how identities goes. So study these particular ident. Now till now you know Taylor series, you know derivatives, but you don't know derivatives for all functions. That's also true. It's not something that you need to know for all. Of course, using curve theory, so if you just look at curves, you can solve it and directly tell that from which particular curve one comes to. But essentially, when you are about at a point where you need to solve equations, then at that particular point, you might have, it's like if you have an understanding of this, it would be easy for you to understand at that point. Okay. Are there any further doubts here?
Ma'am, so
Yes.
basically, whatever derivatives, the standard derivatives that we have now, it
Hmm.
basically has derived from the Taylor series of those functions.
So if you see now that Taylor series also needs derivatives, right?
Hmm. Yeah.
So first you need to know differentiation, integration, and then you go to Taylor series. Because
Okay.
Taylor series was a big jump here.
Hmm.
Because we saw, no, that here, here itself they need you to compute a derivative for a function. That's why I guess in the first lecture, Prof didn't deliberately say that, okay, what this is, and he directly gave us the formulas for the same. That's
Yeah.
why at this point I felt that okay, since you would be introduced to derivatives, it would be easy for you to catch on Taylor series. Now you, since you can do it for simple functions, now when functions like this come,
Hmm.
you'll feel that okay, if you have an understanding about log, then you can solve this functions also. That's why I told that you can study about log also. It's also
Okay.
pretty simple that for log it's like 1 by x if you have different similar rules as differentiation, but you'll enjoy while learning log. It's similar to differentiation. Do it for simple functions. I'm not saying pretty much big complex functions.
Hmm. Okay.
So we'll quickly go through last year's assignment then, and then so that you can solve this week's assignment. Okay. So here, now you see here, for this week they have already given you a ln x here. So that's a log x. Okay, so We'll just see if you have simple ones first, then we'll do the other one. Okay. So let's see the question number 2. Okay, for question 2, you have if f of x is 4x plus 1 and 1 minus x cube, what is the value of f dash of 2? So now you have this function. Now you know product rule here, right? How will you do is like one cases, you can either multiply all of them and then 1 minus x cube. Now you need to know the identity and all. But if you don't want to, I guess I can simply do it on my tablet itself. It would make it easy. Can solve the questions there. Hmm. TF. Okay, this makes it easy for us to solve questions. Two minutes, I'll share my screen. Okay. Okay, entity. Questions. Right. So I guess screen is visible. Okay. Yeah. So if you have this question, just look into it. What you can try and do is that you can either expand this. So for that, you'll have to Google or you will have to know by heart this 1 minus x cube, right? Now, if you don't know that, you have the product rule with you, right? Where you have d by dx of f times g. How you do them is you first differentiate f, keep g as it is, then you differentiate okay, then you differentiate g and then keep f as it is, right? If you do this way, how it comes, let's say if this is our f and this is our g, first differentiate f, so that would be 4 times g would be 1 minus x cube plus, we'll keep f as it is, so that's 4x minus 1, sorry, plus 1, and this is like 3 times 1 minus x and whole power 2, right? This is fine.
Yes, ma'am.
Now we want to evaluate it at this f dash of 2. So add 2 here. 4, 1 minus 2, so that's minus 1 whole cube. Plus this is like 4 times 2, 8 plus 1. This is 3. And this is 1 minus 2 minus 1 whole square. So this makes it positive. This makes it negative. So minus 4 plus this is 9 3s are 27. So this is fine. Answer came out to be ulta. Did we do it right? Answer is negative 31. So we had one more term here. Oh, okay, okay. Now what did we do wrong? Did you see? So here, it's nice we
4x
did.
plus 1.
No, that's fine. So you see here, this one. So when we do it for x, right? What we did it as that we did it as simply sorry 3x. So we did it. So okay, I'll just write it again. For this particular function, when you take derivative of it, we did it as 3 times 1 minus x and whole square, right? Because 3 minus 1 2. But this x has not gone yet. We haven't differentiated x. That's the main function that we did. For x, there would be a minus 1 sign. Okay, so we evaluated the big function and then this one. So this is another rule that is called as chain rule that we saw. I guess it was there in the sheet 8. So this is a chain rule. So you do the outer function and then you see where is your the variable that you want to differentiate it with, and then you have it. So that way this gives us a minus 1 sign here, and hence our answer is negative 31. Okay. Okay, so this is done. Then you have at x equals to 2, which of the following functions has the highest slope? So this is nothing but you'll only have to evaluate it. X cube won't give, x square won't give, x raised to 2 is like at 2, this is 9 power of 2, and this is like a smaller quantity. So only this one can give you a higher slope there. Now, what is the slope of the function 1 plus e raised to x at x is equals to 1, where they have told us this? So this is nothing but 1 plus this particular quantity. So you have this. Oh, at x equals to 1. Okay, now they aren't telling us to evaluate it, but what they are asking us, the slope. So what would be the slope? That would be a derivative of this function. Okay, so this is nothing but e raised to x. Now you have x is equals to 1 and you know e raised to 1 is this, so hence the answer is this. Understood?
Yes, ma'am.
Okay. Then next one, the concentration of a protein in an image of a cell is reported by intensity of pixels given by this. If it is high on the posterior left and low on the anterior right, so posterior left and then you have anterior right, it is higher and low there. Okay. So it's the other way around. Higher on the posterior left and lower on the anterior right. Something as this. Okay. What is the suitable equation here for pixel intensity? Okay. So, okay, that's pretty much straightforward, right? So let's make an image. In this image, they have told us that it is higher on the posterior left. So posterior left, if we just see, it would be this particular region, right? But now this is higher. So that would be this point. Let's say it's like, if it's going from 0 to a maximum value here. And now they are saying that it's low on the anterior right. Anterior right would be this, but it's lower. So it would be this particular region. But since it's lower, it would be this point. So now we have a slope here as this. So these are like the points which are going this way. So we see here that which is a suitable equation. So we don't see that it has increasing or constant. So this is nothing but of course this particular function, which is like decreasing. So if it would have been in this, it would have been x, whereas it's the other way. So hence it's like inverse of x. So that's 1 by x. This was understood? Into 2? It's like it's you don't need to see, but it just you need to check with the option that okay, which one will follow it through. You just need to interpret it that how the equation is telling us to. Okay.
Got it, ma'am.
Then this one. Can you do it for this one? Tell me what its differentiation would be. So it is product rule here. Can you do f dash of x? Tell me what it would be.
So, ma'am, first we'll keep x constant
Okay.
and differentiate e power x,
Which is
x into e.
no. We saw na, for e raised to x, the differentiation keeps as same.
Okay, okay.
And that we did using Taylor's.
Mm-hmm.
Okay, you can look at it again. So that would be e raised to x and then plus
Plus e raised to x.
because x derivatives is 1.
1. Yeah.
So then you do it at x equals to 0. So this becomes 0 and e raised to 0 is 1.
1.
Right. So this is the answer. Then which of the following equation represents a 2D function varying in both dimensions? So which function in both dimension? Now you see here it's only x. This is constant. Gone. This is also 1 plus y square. So only option that is with both x and y. So here in this case, you only had to see a function which is nothing but varying with respect to both x and y. Right. So that's your answer. Directly straightforward. Then here, imagine a 2D image of a spherical cell. Intensity of a protein is 0 at the center. Okay, we'll have to make something for it. Let's see. Okay. Now they are saying that the intensity of protein is 0 at the center. So at this particular point, we don't have anything. And it increases radially with intensity proportional to the distance from center. Okay. So can you sense something from here? It increases radially with intensity proportional to the distance from center. So it's increasing radially. So that means it's something which has a radius equivalent to its arc. So that is similar to how we all used to have a circle, right? When we have a circle, sorry for the asymmetry here, but in this particular case, let's say this one, contrast is poor. So for this particular case, this is like, let's say radius r. Now they are saying that the intensity is proportional to the distance r. So it is nothing but increasing with this point. So how do you represent an equation of radius as? So that is nothing but if you have, let's say this x and you have here this y, if you have this as your radius in between this points or this point, how will you write it as? Your hypotenuse in this particular case. So that would nothing but x square plus y square. So that follows from Pythagoras rule. Oh, Russ. Okay, Pythagoras theorem, where this is your hypotenuse and this is your right angle triangle, right? So now they are saying that it increases proportionally radius from the center. Increases radially with intensity from the center and it is 0 at this particular point. Which of the following expression represent this? So it cannot be this one because both will give you a subtracting function. Cannot be a ratio of them. E raised to x is definitely not because one would be something like this, one would be something like this. So it's not increasing radially from the center, whereas this one. So that's like directly showing you the circles theorem and how the intensity is increasing from this point. Okay? Did you understand this point?
Yes, ma'am.
Then this one. Okay, that's a big question. Imagine two spheres like molecules at a distance x apart. Okay, let's make it so that we can visualize it. So we have like this two spheres like molecules and they have a distance x apart, but they haven't told us. Okay, so there you go. They said that here x is the distance from the center of the molecule to the center of the earth. Therefore, assume x as positive. So x is nothing but from this point to this point. Okay, wait, sorry. X is like this. It's going here and there. Okay, I can move it. Just assume that those are centers there. Okay. So this one center here and this one center here. Right. So this is our X. And these are like two spheres. So let's say sphere A and sphere B. Now the interaction energy between them is represented by potential energy called something. This potential and it has this form. Okay, so that's how they interact with each other. Where this is and this is a positive number, so those are constants. Calculate the force that is negative. Okay, so here you wanted to just to differentiate both of them. Okay, so we have V of x as E. So that's a positive number that they have told us, and it's not function of anything. That means it's just a constant. Okay. Now you have A by x whole raised to 12 minus 2 times A by x whole raised to 6. Okay. Now they told us to evaluate it at A. Now for doing this kind of functions, no, oh, did I wrote it wrong? Oh yeah, this is x. For doing this kind of functions now, you first see that what the original function tends at a, and then you do the derivative of it. You will get an idea that how it is tending to. Now if you see x is equals to a for this particular function v of a, you see that this is a and this is a minus a is 0, right? You don't need to solve this at all. Now I'm telling you why. Now, if you differentiate it with respect to x, this particular term with respect to x, now since v of a is 0, what would be v dash of a? 0,
0.
right? Yes, exactly. Now, when we had to differentiate it and we didn't know this point, then what we would do? Now, you have this 1 by x here, right? Now, if you differentiate 1 by x, how would you do it? It would be x raised to minus 1. So that would be minus 1, x raised to minus 1, minus 1. Similar to x raised to n, that becomes xn and n minus 1. So hence a minus 1. Okay, so that becomes minus 1 and x raised to minus 2. So that is nothing but minus 1 by x square. So if you do it, you'll have to do it this way and then power 2 and then power 2. Eventually, if you do it at a, that would be 0. So don't differentiate unless and until you see the original function itself. Try and evaluate it at that function. Okay. So for this, it is 0. Now this one. This one is bit, you'll have to solve it. So this is like you have been given. So there are two ways to solve this one function. Okay. What you can do is like assume y as 1 plus x square by 1 minus x square. So you can assume it has two rules. There can be two rules to solve it through. You can either do a product rule or you can do a division rule, or how you call it as a quotient rule. So assume that either the first function is u. So in this product rule, if you want, so u times v, or you can do it as 1 plus x square by 1 minus x square. So that would be nothing but u by v. If you do it this way, it would be, so first derivation of, let's say you keep u constant and this plus it is like if you write first term and second term here and there, it doesn't matter. And you take this one. So if you want to do this way, you can do it this way. Or if you want to do it this way, there's like another rule for it. So you first take u, then you subtract it, keep u here, differentiate v, divide it by just take v square, right? That's it. So now if you know both of them, here you see you have u and v, right? U and v both are there together. Now eventually you have 1 minus x square. Here also you have 1 minus x square. So now you know that the denominator will have 1 minus x square ka whole square. So you have this option, this has option, this has option, this is cancelled over here. To do the rest, you'll have to solve it. There's no other stepping back from it. Yeah. So either you do a product rule or a division rule, you can solve it. So let's say if we want to solve it, I'll show you the division rule because you already know the product rule here. So now you have u. So you know differentiation here. So 1 minus x square and then differentiate this u. So that would be 2x, right? Minus u is constant. So that's 1 plus x square. And you differentiate v. Now what would be the differentiation of v here, Aditi?
Minus 2x.
Exactly. That would be minus 2x. And divide by, we have v ka square. So 1 minus x square whole square. So this one you have 2x minus 2x cube minus minus plus 2x, and then you have minus minus plus, sorry, this minus minus, so that's plus. So this whole will be plus. So plus 2x cube by 1 minus x square whole square. So now we see over here, this is plus, this is minus, and you have 4x by 1 minus x square whole square, right? So that's your answer. So this is done. Now we'll go to the very first question, that was log here. Now how to solve log? So if f of x is equals to x times ln of x. Now, how do you see it? This is ln of x. Naturally, you see log as this log of x. This is how you'll see in textbooks, or even whenever you directly search it. There's only a difference to the base here, the base that you're evaluating it at, this one. When it's natural log, when I say natural log, that means this ln of x. What that ln of x means that it is log base e to the x. Okay, it's like that. Then when you have just log, I don't know how they call it, but that is nothing but log base 10 and then your argument is x. So that's the difference in between both of them. Now you have this natural log here. Now if you want to take a derivative, this is product rule, right? Now you first take for x. So x is 1, keep ln of x as constant. Plus, now you'll have to do is like, you'll have to keep x and then you'll have to do for ln x. So the derivative of log x is 1 by x. So that's why I was saying that learn log. So I guess perhaps in next session, I can introduce you about log and the properties of log. But for now, you can just remember this formula that derivative of log x is 1 by x. Okay. So when we do for 1 by x, so this, and then so the answer comes as this x is cancelled and this would be 1 by log x. Okay. This one. Any questions?
No, ma'am.
So you will be able to solve this week's assignment then?
Yes, ma'am.
Okay. So that's it for today then. We'll meet next week then. Okay.
Sure. Thank you, ma'am.
Thank you. Bye.
Bye.